Wow, I'm so impressed. I'm almost speechless. Hi, I'm Emily, and I'm going to attempt, through a haze of severe jet lag and maybe too much sake last night, talk to you about do-it-yourself testing. Let me just adjust this a little bit. So we lovingly refer to do-it-yourself activities in Berlin as DIY. Berlin, if you've been there, is a city that really loves crafts and using your hands and kind of artisanal activities. So it's kind of appropriate that I live in Berlin and I'm talking about do-it-yourself testing. How many people, before I get started, are users of MongoDB, just out of curiosity? Wow, not that many. Okay, you've heard of MongoDB, right? It's an open source database. It's a document database. You can describe the documents it saves as kind of like JSON documents, but we refer to the data type as BSON. So it's loosely binary JSON. It's not exactly JSON, but it's similar. So it's keys and values, but they're rich documents, so you can have embedded documents and arrays, so lists as values in your document. So as I think Jonan said, I could pick out some of the English words. I'm a Ruby engineer on the MongoDB drivers team. So I'm employed by MongoDB, the company behind this open source database, to work on the Ruby project. I'm based in Berlin, and I'm from New York City, where MongoDB is based. You may know my code through the following gems: bson, mongo, mongoid, bson extension, mongo Kerberos. And just to give you a little bit of information about each one of those gems, so maybe you've seen it before, and with some context you might recognize it. Bson is the gem that does the serialization and deserialization from Ruby hashes to Bson documents. Mongo is the actual driver itself that we rewrote on the Ruby team over the last year and a half. So the version 2.0 is a complete rewrite, and there was a version, the 1x version, available for a couple of years. And Mongoid is the active record replacement if you're using MongoDB with a web framework, usually Rails. Most of our users on Mongoid are Rails. And then Bson extension is a way to make an older version of the Bson gem faster. Mongo Kerberos is a gem that nobody uses because nobody uses Kerberos, really. Anyway, so those are the gems I maintain, and I work for MongoDB on these gems on the drivers team. So the drivers team at MongoDB, this is us. We're about 22 people, kind of spread around the world in different places, and we collectively maintain 10 different drivers, so 10 different languages. And as you can see from this list, the languages are not all static, not all dynamic. They're very different languages, and we all program in very different ways in each one of these languages. MongoDB, if you're familiar with it, and if you're not, we were known in the beginning, and we got adoption pretty quickly a couple of years ago because we are known for a really good user experience. And part of what made us have such a good user experience or developer experience was that we offered drivers in each one of the major languages. So as you can see from this list, whatever language you were programming in, we offered a driver pretty early on for that language. So we're able to really get adoption and popularity, even though the database itself was pretty immature at the time. It was a pretty new project. We became well known quite quickly. So what that means is that drivers make up the interface to the database. You can't use the database without a driver. The driver is the thing that does all the serialization. It knows the wire protocol. It knows the format of messages to send to the database server. It knows how to interpret the messages coming back. And each one of these drivers does pretty much the same thing, just in a different language. So collectively, you can talk about a driver to MongoDB as the interface to the server. As I said, we have 10 official drivers. There are more drivers in the community. We're not the only drivers available, but we're the people who are paid by MongoDB to work on these drivers. And the drivers themselves, as I said, we got adoption pretty quickly because people would build drivers in their language communities to make people be able to use MongoDB. So many of the drivers we ended up with as a company over time started as open source projects. what happened, the history of this is that people would build these drivers in a certain community, and then we would notice that it was getting popularity and say, oh, maybe we want to hire this person and pay them to work on this driver officially, or we want to somehow adopt that project and work on it internally. So as you can imagine, the reality of this situation is that all of these drivers grew pretty organically. They overlapped in terms of the features that they provided, in terms of how they behaved given changes in a cluster. So when you have a MongoDB database, you don't always just have one single server. As I'm sure you know, if you're a web programmer, you'll have a cluster. So you'll have a replica set or a sharded cluster, which is a collection of replica sets or a cluster of replica sets. So the driver needs to adapt to changes in your cluster state and detect when a certain server goes down and adapt to that and adjust its own view of the cluster. So each one of these drivers kind of did the same thing. Behavior was kind of all over the place. We wrote no specifications in the beginning because, as I said, we just kind of accumulated or collected these drivers that were already existing as open source projects. So what that means is we made up a pretty ugly interface to the server because we were no one driver was particularly bad at being an API to the server, but if you talked about drivers collectively at MongoDB, you couldn't really talk about them as one single project or product. So for example, a support person who was maybe trying to provide support to one of our clients would be asked a question, does a MongoDB driver support this one feature? And they'll have to say, oh wait, let me check with the driver engineer. I'm not really sure, like the C++ driver does this, but I don't know what the Ruby driver does. So we made up this like really ugly bouquet of flowers, essentially. We're all different shapes and sizes. We weren't coherent, and you couldn't really talk about the interface to MongoDB in one particular way. So we had to do something about this. MongoDB as a company grew up over the last couple of years. We hired a lot of people. We got a lot of traction. We got increasing numbers of contracts from clients, so more people paid for our services, which are consulting, support, training, kind of a typical open source business model. And we realized about 2 years ago, like we really have to get more consistent across drivers as to how we behave and how we document our drivers. So some drivers rewrote their driver. In the case of Ruby, that's what we did. Other drivers did a huge refactor of their code base, which is what Python did. Java rewrote the driver. And along with these rewrites, we got together as a team and we wrote specifications for how the driver should behave. So although we're writing languages that are very different from each other, Java, C#, Python, we're all so different from each other, we wrote text and clear, it's almost like a law document. We use specific words like must, like maybe, should not. So we use these very specific words to write our specifications. And these specifications guided the design in either the refactor or a rewrite of each of the drivers. So this was even more important or more significant because as MongoDB became mature, we would have clients who were larger companies, and in larger companies like a bank or a big, maybe even like a governmental agency, sometimes they'll have different projects in an organization that use different languages. So engineers would switch between projects and have to switch drivers to MongoDB because they're using the same data store, but they won't necessarily have the same features supported by their driver. So writing these specifications allowed us to redesign our drivers and really become one as a team across 10 different languages. So this revamp allowed us to, we've all released our drivers over the last year, except for one team that's kind of lagging behind a little bit. But for the most part, we've all released brand new drivers. The Ruby driver came out in March, version 2.0. And now I think of us as this really coherent, beautiful bouquet of all the same flower, maybe in different colors. So there's not so much chaos or difference going on between drivers. The reason I'm talking about these specifications so much is because Two reasons. One, as a collective team, we were really happy to have a document that we could all refer to that described our design. It served as documentation to us internally, so we have sometimes new hires on our teams, or we want to talk to each other about how our drivers behave. And before, there was a lot of mystery as to how the other drivers behave, so it made it difficult to learn from each other. But now we have these specifications that are in this GitHub repository. It's all open source, and we're really proud to have this because we want to be more clear and provide more transparency into how our drivers work, as well as allow more people out in the community to build drivers, or at least say, like, my driver is compliant with the MongoDB specification for this one particular behavior. So I think that's really great for us as a team, as well as for the community. This one specific specification that was the first one we wrote is called the Server Discovery Monitoring Spec. This spec, we call SDAM for short. It describes, the definition is the logic required to make an application using MongoDB highly available. What that means is it's the algorithms and the design and the interpretation of messages that you receive from a server when you ping it to get its status, and what that means for the driver's view of a cluster state. So when you have a cluster, the driver will ping each one of the servers, get a state back, and then interpret that to have its own view of the state. And it needs to have that because depending on what operation your application is doing, the driver needs to know where to send that operation. It could be a write, it could be a read, it could be an administrative operation like building an index. So all of this information is critical for the driver to work. This also was the darkest corner of each one of the drivers. This was the place where we had the most number of bugs. This was the hardest code to write. It was the most inconsistent between drivers. So this was the first spec that we wrote. It was written largely by my colleague Jesse Davis, who at the time was maintaining the Python driver. He's now working on the C driver. And if you're interested in looking at how our drivers work, it's a really good document for understanding really like the core of the driver, the most important, probably most complicated code as well. So this was great. We wrote this specification. We went on to write other ones. This one we were really proud of because it gave us a starting point to really work together as a team. But what next? How do we actually make sure that each one of our drivers complies with this specification? Sure, we wrote all of this out in text in this kind of law document format, with kind of ordering that each driver should have this behavior. But how do we actually make sure that each driver does this when we're working with 10 different drivers? So how do you validate compliance when you're working with so many different languages and you're working off a document that's text? When we sat down and tried to decide how to solve this problem, we realized that we had a bunch of requirements for how we were going to tackle this testing problem across so many different code bases. We knew we had to have unit tests, but unit tests weren't good enough. Unit tests could test that given a certain response from a server, the driver adapts its state to that response. But we also needed integration tests because drivers work with a database or a collection of servers. Those servers can be in any number of states. The number of states is enormous. So we have to be able to replicate or reliably reproduce these scenarios in a MongoDB cluster. And with certain servers in different states where their state is mutated throughout some period of time, and we need to test our drivers as they adapt to that change. So how do you do that? That was a really difficult problem for us to solve. So we decided that we would build our own test language, test format, and test framework in each one of the drivers. But the tests themselves would be shared amongst 10 different languages. So how do we do that? We kind of refer to it as do-it-yourself testing, or we built this custom test framework for ourselves. And I'm going to share that with you and hopefully maybe help you think outside the box because Ruby has a lot of testing frameworks available. The Ruby driver prefers to use RSpec. We've used unit tests and mini tests in the past. we have testing frameworks available to us, but there are some scenarios in which you might want to build your own testing framework. So I'll share with you our process of doing that and share some ideas and some things that we considered when we built this, and it might help you realize where you might want to do this in your own code bases. So our approach, DIY testing, we first had to define a format, and we chose YAML, and I'll explain why in the next slide. We had to actually define the structure of a test. So how do you describe a test in YAML? What semantics are we going to use and stick to across hundreds of tests? And what scenarios do we actually have to test? So once we have the format, the structure, what are we actually going to test? What is important to test? So along the subject of YAML, we chose YAML because it describes data. We needed something that was static. It could not be programmatic because, again, this needs to be interpreted by 10 different languages. It needs to translate to action, so we need to have these static words or symbols that translate into something the driver can do, or as you'll see later in integration tests, it needs to translate to an operation on a MongoDB cluster. Most languages have a YAML parsing library, so there's no extra coding required there for a particular language. Driver authors can write a reusable harness. So I refer to a harness is essentially the thing that reads in the YAML file and interprets it as a test and then runs a test and passes and fails, returns pass or fail at the end. So we need to write this reusable test harness because we're going to be testing many different components of the driver, not just the SDAM or the server discovery and monitoring behavior of the driver. We're testing many different things. So you want to make your harness as generic as possible so that like me as the Ruby driver engineer doesn't have to rewrite the same code every time there's a new set of YAML tests. And what I think is really cool about this, or one of the most important, and what was a huge improvement for our team, is that as we made changes to this spec document, we could couple those with changes to YAML files or additional YAML files that would kind of signal to a driver that there were changes in the spec. So if I made a change in the text of the document, I could pair that with a change to the YAML, and then the drivers running these YAML tests would know immediately, oh, there's been a change to the specification. So it's a way of kind of pushing out like a notification to drivers about changes to the spec. The specs is a living document because MongoDB obviously is being developed and its behavior changes over time. So we sometimes need to adapt our driver behavior to correspond with that. The test requirements themselves, we needed to build unit tests, and we needed to build integration tests. Integration tests is not that simple. Unit tests was not too bad because we do a lot of mocking. It really has to do with just interpreting responses from the server, so we can just mock getting response from the server. So I'll talk about unit tests first to kind of warm you up to the idea of defining tests in a YAML format and how we interpret those. And then I'll go into integration tests because that involves a separate service we built, which I think is really cool. And I'll show you a screencast of how we use that service that you can actually use if you're a MongoDB user as a testing kind of puppeteer that starts MongoDB clusters for you. So starting with unit tests, let's look at an example of a unit test defined in YAML that each driver interpreted and ran against its code base. This is the most simple example, the most simple MongoDB cluster or server that you can have, setup that you can have. It's a standalone. So this is describing to the driver that you're going to ping a server, get a response back, and it's going to indicate that there is only one server in your MongoDB cluster. It's healthy, it's up, and you're going to, at the end, have your state say, I have a direct connection to a standalone. So the structure of the YAML is there's a description of the test, there's a URI that the driver uses to instantiate an instance of the client to the database. There are phases which describe you'll see in a further example that you can have many phases, but in this case there's only one response. That indicates the driver pinged a server, got this response back, and then at the end is the outcome. So the outcome state of the driver is it knows it has one server, the type is standalone, and then the whole driver's view of this cluster of one server is that it's a single topology. So that's the most simple example, and that's how we describe this test. And each one of the drivers can interpret this and run that against their driver using their test harness. In the Ruby driver, this is how we wrote the test harness. I have, it's a lot of code, but I have a screencast where I'm just going to scroll down and show you the components of it. On the top, we have, so this is a file that describes 4 different objects that are instantiated after interpreting that YAML file. So this is part of the test harness. The beginning is some custom matchers that we use with RSpec. And, oh, okay, it's going. And then this is some global helper methods. And then the spec object is the object that reads in the YAML file you'll see in that line there and assigns it to a variable called test and then creates phases out of it. And the phase knows how to get responses, and then there's an object wrapping the outcome. So each one of these can be interpreted, and methods are called on these objects in the course of running the RSpec. And the custom matchers we wrote interprets the state of each one of these objects and verifies whether or not the test has passed. So this next screencast will show you the actual RSpec file. So the file, I guess, is that, here we go. Maybe I didn't update this slide. Okay, well this is the actual spec itself. Yeah, the name of the file is server discovery monitoring _ spec. I forgot to update the name. But what it does is it goes through each one of the YAML files. It reads it in and instantiates a spec object from the, yeah, up there. You instantiates a spec object from that YAML file and then goes on to run the test. And you'll see towards the bottom where we use the custom matchers and we test the topology type of the client. So the client is the instance of the driver client. And then we test here for a replica set, we test to make sure it's the right topology type, it has the right servers. It tests to make sure the replica set name is correct if it is a replica set, et cetera. It's probably too much code to really parse right now looking at the slide, but it's just to give you an idea of how we instantiate these objects out of the YAML file and then use them in an RSpec test. So this is a little bit more involved. This is, again, another unit test, but it's testing the topology replica set type. So what this does is the same exact thing, so I use the same exact harness, but it's a little bit more complex in that the URI indicates that it's a replica set by using a replica set name. The phases is one response from one server that indicates there's more than one host. And then the outcome is that there are 2 servers actually known to the driver in its state. The first one is a primary, the second one is unknown because it hasn't pinged it yet, and the resulting topology type is a replica set with a primary. So those are unit tests. We're not actually sending any messages to any servers. This can be run with no MongoDB running. These are just responses mocked from servers, and this is testing the behavior of the driver, its ability to adapt to changes based on responses back from servers in a replica set, or a MongoDB cluster, rather. So back to these test requirements. Those were the unit tests. They're not too interesting to talk about. It's just basically YAML. We wrote this test harness, and then we run them in our RSpec tests. Where I think it becomes more complex and also more interesting is when we talk about integration tests. The hardest thing with integration tests was the ability to, as I said, recreate these scenarios where every single server in a particular cluster has an exact state that we define up front, and then we want to manipulate the cluster in some way, test the driver against it as the cluster changes, and make sure the driver adapts accordingly or adapts correctly. So if you have a replica set, in our replica sets we have one primary that takes writes and multiple secondaries that don't take writes. So if you have a replica set and the primary goes down, you expect the driver to detect that and not be able to, not try to send writes to the primary. Things like that. So what we did in order to address this problem of not being able to create reproducible reliable scenarios, just in our own code, was building a service called Mongo Orchestration. And I'll go into a little bit more detail about Mongo Orchestration because I think it's a really good tool that we built. And if you want to try it out, you can actually use it. It's open sourced. It's basically just, as I said, a kind of puppeteer that creates MongoDB processes for you. And the MongoDB processes are real MongoDB processes. They're not baby testing MongoDBs, but I think the interface, the HTTP interface to it, the RESTful API is really useful in any driver, any language. A little bit more about Mongo Orchestration. It is implemented in Python. You can check out the code it's MongoDB/Mongo Orchestration on GitHub. And you can manipulate clusters via a RESTful API. And this next slide might not be that relevant because there aren't too many users of MongoDB here, but I wanted to point out that it's not our product called automation. Automation is something that people pay for that allows them to start real MongoDB processes on servers wherever they are, and it's used in production, and it has checks in there to make sure that best practices are followed as you do operations on your cluster. Mongo Orchestration allows you to do whatever you want. It starts, it doesn't protect you against fault. It lets you do fault injection. So it allows you to kill your primary. It allows you to do upgrades whenever you want. It doesn't have any checks to protect you against any mistakes. It's intended for testing. It starts all of your processes on one machine, so it's definitely not supposed to be used in production. But I just wanted to point that out in case you are familiar with the products of MongoDB and you were wondering why we had Mongo Orchestration for free and why you wouldn't use that over automation, why you would ask people to pay for something like automation. They're totally different things. So back to Mongo Orchestration, you can use this service, the RESTful API, to this process running to build a single cluster topology, a replica set, or a sharded cluster, just by sending it a JSON document. So we'll look at how you actually do that, because I think it's really interesting and really great. This setup, this is how you would do it in Ruby. I usually just use a Ruby console when I'm using it for testing. I define a config as a hash, and I use HTTP party, and I send a post request to the URL of the service, and I send the config, and it creates that cluster for me. This is what the document looks like that you send to it as the payload or the body of that post request. This is for a single server. The only thing that's required is the name because you need to specify the name of the process. In MongoDB, when you start a process, it's either a MongoD, which is a server. Those are servers, members of a replica set or a single server, or a MongoS. A MongoS is the router in, and it's that rectangle there. So it's the router when you have a sharded cluster, and it knows where to send route messages, but the driver actually talks to the MongoS. So that's the single server. This is a replica set. There are a lot of options here. All of these correspond to command line flags. So if you were to start a MongoD process or a MongoS process, all of the flags that you have on the command line are the flags correspond to keys in this config document. With a replica set, you also have members on the bottom where you can describe parameters that you can have for each member of your replica set. So if you're familiar with MongoDB, you might recognize some of this. You have priority. You can start them on particular ports. You have options hidden, SSL options, et cetera. And then also with a sharded cluster. So depending on what kind of config you send to the service as a post request, it'll start one of these clusters for you. So it's super simple, really easy to use. And as I said, really lightweight. There's nothing too crazy that you can do with this or too complicated about using it. And the one last thing that's really cool about it is that you can, when you start the Mongo orchestration process, you provide a config file, and the config file has, you can list in it any number of binaries corresponding to a key that is a particular version of MongoDB. And where this is really great is when you start, remember that config that had the list of members in a replica set? You can start a replica set pointing to different binaries. So you can have different versions in your replica set, which is actually a real world situation. Some people have replica sets where some of their members of the replica set are different versions from others. So we use this for, we call it multi-version testing. So now I'm going to show you a screencast that shows you kind of the life cycle or the steps that you would take to use Mongo orchestration for testing. It's about 5 minutes, so it's a little bit long, but I think it's useful to see how it works. So I'm going to start the service right now, and I'm not passing a config file, I'm just starting it, so it'll use the default version of MongoDB. And I open a Ruby console, I'm requiring HTTP party, and I'm going to create a base URL that I'll use throughout the rest of the screencast that points to the service running on port 889. Next, I'm going to do a GET request and see what URLs I have available to me from Mongo orchestration. And these are, you can get information on what sharded clusters you have, replica sets. So you can start different clusters with the same service. It's not one-to-one. So I create a URL for a replica set. I will send a GET request to see if I have any replica sets running. It'll return an empty list. And then I'm going to copy a config that I'll show you later in a slide for our YAML tests, for our integration tests. I'll show you in more detail slowly what that is later on. And I'm going to send that as the body of the post request to start a replica set. So I'll use the URL for a replica set, and I'll send that as the body of the request. And Mongo orchestration will block until that replica set is created. And this is critical for running tests. You'll see a little bit of code later on in our Ruby tests where we had a test runner that would try to start a process and like ping the process and see if it's up. But we had to have this loop that like randomly went 80 times just seeing if our replica set was started. But it's really great with Mongo orchestration that it just blocks until the replica set is ready for testing. I'm looking at the time. I don't have so much time left, but I think I'll actually skip over the rest of this and go through the rest of the slides because they might be more relevant to the point of do-it-yourself testing. But basically what I'm going to be doing throughout the rest of this is I'm going to send a request to kill the primary, show how the primary is killed, and then restart the primary. So this will be available in the slides later on if you want to watch the rest of the screencast. And the documentation for Mongo orchestration is great as well. So you can check that out too. I went over the benefits of Mongo orchestration before. It allows reproducible test scenarios. It's really easy to use. And it allows us to do multi-version testing, SSL testing, authentication, anything we want. And this is the code in the Ruby driver it's a tiny bit of code in this enormous file where we're trying to start a replica set ourselves. And what was really difficult about it was that MongoDB has a lot of different names for flags depending on the version, and Mongo orchestration abstracts all of that. And in this code, we had to write so many logic statements about if it's this version, then do this, and blah, blah, blah. So this was really ugly code that we're able to just completely get rid of in every single driver. Jenkins testing is an enormous matrix, so Mongo orchestration allows us to test any number of configuration. And I will skip through some slides pretty quickly. I will show you now an example of a YAML integration test using Mongo orchestration. We define the config for the service. That's what I copied and pasted into the config sent to the post request. There's a client setup for the driver, and this is a continuation of that file. And then there's some phases where it goes client operation, then there's a request sent to Mongo orchestration service that manipulates the cluster, and then another client operation that has an outcome. And the driver does this operation, and the test runner will know whether or not the test passed or failed based on what the expected outcome is. So I'm going to skip through this and just get to the end where I describe how to build your own testing framework based on what we learned as a drivers team doing this for 10 different languages. Ask yourself, is it unit or integration tests? What are you building? How should your tests be defined? What format do you want to use? Does it need to be language agnostic? And is it directly related to specs or documentation? Is there a way you can generate these tests from your documentation? For us, that would be really cool if we could just generate from the text description of our specifications these YAML files. You'll need a resource, which is a wrapper around the external component if you have one, specification object, which is the parsed YAML, a state manipulator, so it's something that processes all those phases that you have in your test, and then the test itself, which can be executed and has a pass or fail outcome. Make the test runner as generic as possible so that you can reuse it. And if you want to use Mongo orchestration, if that's appropriate for your project, maybe there are other services out there like this, provided by other data stores or other services that you would use. And I want to end on a note that we spent a lot of time doing this. I'm really proud of having put in so much effort over the last 2 years of writing specifications and collaborating to write these tests. And we're happy to provide all of this to the community, and hopefully it'll help other people to maybe think outside the box and build their own test frameworks or use our tests themselves or use Mongo orchestration. So that concludes my talk. I have some resources on this URL that are some of the repositories I referred to. That's me on Twitter, and I'm happy to answer questions later on or talk about MongoDB in general, anything. Thank you.